Hello and welcome. In this video, we're going to talk about what a polynomial function is, what standard form is, how to evaluate a polynomial function and its end behavior, and then how to put all those things together to create a sketch of a graph of a polynomial function. So let's go ahead and jump right in. A polynomial function is a monomial or a sum of monomials. So it's a bunch of terms being added together. We have been looking at quadratic functions, and a quadratic function is an example of a polynomial function. So a polynomial is a monomial or sum of monomials. So an example of a polynomial would be 2x squared plus 5. A polynomial function means that instead of just saying 2x plus 5, we're saying that is equal to f of x or equal to y. So a polynomial function is of the form f of x equals a times x to the n plus some other number times x to the n minus 1 plus ... until we get to a constant. So key things about those exponents, those different n's, they need to be whole numbers, meaning greater than or equal to 0, and the coefficients are real. So if the exponent is negative, if the exponent is a fraction, that's not going to work. And then the easiest way to do whatever it is that we need to do with a polynomial function is for it to be in standard form, which means that our exponents decrease. We start with the largest exponent and we go down. So x to the 5th plus 2x to the 3rd minus x squared plus 5, something along those lines, where our exponents, they may not be one right after the other, like there are some that are missing here, but they decrease, and then the final value that's being added is our constant. And again, if we're calling this a function, we need function notation in front. So we've actually worked with polynomial functions quite a bit in this class and in previous classes. We've talked about the constant function, so that would be like f of x equals some number for negative 14. That would be a line, a horizontal line. We've talked about linear functions like y equals mx plus b, or in this case a1x plus a naught. That's going to be a line. We've talked about quadratics, spent a lot of time talking about quadratics. A cubic would be degree 3, a quartic would be degree 4. And the degree is just that largest exponent, and then we want to make sure that's the term that's written first for it to be in standard form. So the degree is just the largest exponent. So what we're going to do now is we're going to look at some functions, and we're going to decide if they're polynomial functions. We're going to write them in standard form if they are, and we're going to talk about what type they are and what the leading coefficient is. All right, so if I look at number 1, I'm looking at those exponents first, 3, 4, constant. Those are meeting the requirements that we requested for exponents. So this is a polynomial function. If I want to write it in standard form, I'm going to write it with the highest degree term first, so the square root of 2 times x to the 4th. And notice the square root of 2 is just a number that's being multiplied in front, minus 0.8 times x to the 3rd minus 12. There's my standard form. My leading coefficient is going to be the number that's in front once it's in standard form. So my leading coefficient is going to be the square root of 2. The degree is going to be this largest exponent, which is 4, and if it's degree 4, it has a special name. It's called quartic. Okay, if we look at number 2, what I notice, x squared, x to the negative first, and I have an issue. We are not allowed to have a negative exponent, so this is not a polynomial function. What about number 3? Is number 3 a polynomial function? So the first thing I'm doing is looking at those degrees, 2 and x. Well, x is not a whole number, so this is also not meeting the requirement to be a polynomial function. So here it's because we have an exponent in the variable. And on number 2, it was because we had a negative exponent, or the exponent was not a whole number. So now that we've talked about how to identify what a polynomial is, let's talk about how to evaluate a polynomial function. And this is actually something you have been doing for a really long time. We're just going to formalize it a little bit. So here on number 4, we have a polynomial function. I see that it's degree 4. I see that the leading coefficient is 1 because it's already in standard form. And we are being asked to evaluate that when x equals 3. And we've been doing this with quadratics with any function. We can always make a table of values to sketch a graph. So all we're being asked to do is to plug 3 in for each of our x's and simplify. So f of 3 is going to equal 3 to the 4th minus 8 times 3 squared plus 5 times 3 minus 7. So f of 3 to the 4th, well, 3 times 3 is 9. 9 times 9 is 81. So this is 81 minus 3 squared is 9 times 8 is 72 plus 15 minus 7. And if we simplify this, we're going to get that f of 3 is 17. This notation could also be written as we have identified the ordered pair. 3, 17 is on that function. So go ahead and complete number 5 on your own. Make sure you're following the correct order of operations and then unpause the video when you're done. So here we've plugged in 2. Remember, this negative happens after I put something to the 4th power. So this is negative 2 times 2 to the 4th is 16. 2 to the 3rd is 8 times 6 is 48 minus 6 plus 11. So this is negative 32 plus 48. Plus 5, which is going to be 21. So we can write it using function notation. We can also identify that we have this ordered pair on our graph. So the purpose of being able to plug in values is to help us sketch a graph. But let's talk about something else that's going to help us sketch a graph, and that's going to be end behavior. Polynomial functions are unique in the sense that they are predictable. They have patterns. Just by looking at the original function, there's a bunch of pieces of information that we can pull out right away. And when you get to calculus in the future, there's a bunch of information that you can find really easy and efficiently from a polynomial function. But let's talk about what we can identify from just looking at a polynomial function that's written in standard form. And that's going to be the end behavior. So the end behavior of a function is what happens as we approach positive or negative infinity. So basically it's what is happening at the ends of the graph. If I'm looking at my graph, is it going up forever in both directions? Is it going down forever in both directions? How is it behaving? And again, for polynomials, it's very, very predictable. If you have a polynomial whose degree is odd. So for example, x to the 3rd power, odd degree. If the degree is odd and the number in front, the leading coefficient, is positive, the graph will always go down forever as x gets smaller and go up forever as x gets bigger, which should make sense. If I plug a negative number in here and I cube it, that's going to keep getting more and more and more negative. The bigger the negative number, the bigger that value is going to be. Similarly, the bigger the positive number, the bigger that value is going to be. Now, if the degree is odd, but our leading coefficient is negative, then the exact opposite is going to happen. If I plug in something like negative 3, I'm going to now end up with positive 27 because I'm going to have that negative sign 4 times, 3 times from my exponent and 1 time from this up here. So as my x's get smaller, my function gets bigger. And as my x's get bigger, my function gets bigger. How we write that is as x approaches negative infinity. So as my x's go forever to the left, what's happening to my function? My function is getting bigger. It's approaching positive infinity. As my x's go forever to the right, looking at my x's getting bigger, my function is going down forever, which is negative infinity. So odd functions are going to do opposite things at positive and negative infinity. Even functions are even more predictable. An even function, which would be like a quadratic, which we've been looking at, or like x to the 4th power, is going to do the same thing at both ends, because what happens if I put something to an even power? I always get the same sign out. So if the leading coefficient is positive, both as I go to infinity and as I go to negative infinity, I'm going to be increasing forever, right? If I plug in -5, I get something really big. That's positive. If I plug in +5, I get something really big. That's positive. So just like a quadratic, what happens at the ends as we go to plus and minus infinity is the same. So if there happened to be a reflection or a negative value in front, like -x⁴, or even more simple, like -x², we know that that's going to go down forever. And what that means is, as x approaches negative infinity, so does the function. As x approaches positive infinity, the function still is going down forever. And if it is the same, because it's even, you can actually combine that to be one statement. As x approaches plus or minus infinity, f of x approaches negative infinity. So this notation is going to feel a little odd at the beginning, but you'll get used to it, and really we're just describing in words what we're seeing mathematically happen in the function. So when you're doing this, the key things you need to think about: first, make sure that it's written in standard form so that you can find the degree and leading coefficient. Then you're going to look at the behavior based on that degree and leading coefficient, and you're going to interpret it with a statement or statements about what happens as x approaches negative infinity and what happens as x approaches positive infinity. So let's go ahead and look at these two examples. For number 6, it's in standard form. The degree is 4 and the leading coefficient is negative. The degree is 4 and the leading coefficient is negative. So I'm asking myself, even degree means it behaves the same. This negative in front means that it's going to go down forever. So as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches negative infinity. So as I go forever to the left, the graph is going down forever. As I go forever to the right, the graph is going down forever. Or you can combine, since it's an even power, you can write this as x approaches plus or minus infinity, f of x approaches negative infinity. Okay, number 7. If you want to try on your own, I suggest you pause the video. Otherwise, we can work through this together. We have in standard form to the third power, so degree 3, positive leading coefficient. What that means this looks like is it behaves like the regular old cubic function, which looks like this. So if we're describing our end behavior, as x approaches negative infinity, as I go left, my function is going down. So f of x approaches negative infinity. As x approaches positive infinity, as I go right, my function is going up. So f of x approaches positive infinity. Now we can't combine this to be one statement because it's doing different things, right? It's going down on one end and it's going up on the other end. So now that we've talked about end behavior and we've talked about plugging values in, let's go ahead and put these two things together to talk about how to sketch a function. Okay, so here are the steps that we're going to take when we are sketching a polynomial function. The first thing we're going to do is you're going to make a table of values. These functions all behave differently. Where they rise and fall is not going to be exactly as precise as it was with a quadratic. So you're going to need to make a table of values. You're going to need to plug in as many integer values as you can fit on your graph to get the basic shape of the graph. Then you're going to connect the points to make a smooth curve and ensure that your end behavior is accurate. So let's actually start by identifying what that end behavior should be, since we just talked about that. So what I want you to do is pause the video, look at, these are both in standard form, so look at the degree and the leading coefficient and decide what the end behavior is going to be for number 8. Then unpause the video and see how you did. All right, so here's our end behavior. The degree is odd and the leading coefficient is negative. So on the left-hand side, it's going to go up forever. On the right-hand side, it's going to go down forever. And that's going to be something I want to keep in mind when I'm sketching my graph. Now I'm going to need to make a table to plug in values. And I'm going to just start with -3, -2, 0, 1, 2, 3, because I want a wide range of points because these functions behave differently than just a quadratic function. What I'm also going to do is in my table, I'm going to leave room. I'm going to make a third column that is just where I'm actually doing the work. That's going to help me stay organized. So if I plug -3 in, I'm going to get the opposite of -3 cubed plus -3 squared plus 3 times -3 minus 3. So this is going to be positive 27 plus 9 minus 3, and that's going to end up giving me 24. Now the point -324 isn't going to fit on my graph, but I should keep that in mind that it would be way up here somewhere, so when I'm connecting those dots, I need to make sure I'm not going too far to the left. All right, now I'm going to plug in -2. I'm going to use a different color. When I plug in -2, I get the opposite of -2 cubed plus -2 squared plus 3 times -2 minus 3. So this is going to be positive 8 plus 4 minus 6 minus 3, and that's going to give me 3. And that is going to fit on my graph, -2, 3. -2, 3 is going to be right here. If I plug in -1, I'm going to get the opposite of -1 cubed plus -1 squared plus 3 times -1 minus 3, or 1 plus 1 minus 3 minus 3, which is going to give me -4. And I can go ahead and plot that point, -1, -4. I don't really need to show any work to plug 0 in. If I plug in 0, I get -3. So 0, -3. If I plug 1 in, I'm going to get -1 plus 1 plus 3 minus 3. That's going to give me 0. If I plug 1 in, I'm going to get 0. And then I have 2 more to try and fit in here. If I plug 2 in, I'm going to get -8 plus 4 plus 6 minus 3. And that's going to give me -1. So 2, -1. And then if I plug in +3, I'm wagering this is probably not going to fit, but I'm going to get -27 plus 9 minus 3, and that's going to give me -12. It's not going to fit, but I can keep in mind that that would be somewhere down here. Now you're going to play connect the dots, and you're going to keep the end behavior in mind, which my 2 red dots do sort of agree with the fact that I should be going up forever on the left-hand side of my graph and down forever on the right-hand side of my graph. One thing I want to point out is that we are sketching a graph here. Just because at the green point that you can see on my graph, somewhere from here to here I'm changing directions, right? That doesn't mean it's happening at this particular green point. It could be happening somewhere in between these two. It could be curving around a little bit more to the left. So we're creating a sketch based on the information that we have. It's not going to be perfectly accurate, but it's going to give us enough information. So when I play connect the dots here, I'm going to keep in mind all of those different pieces. Okay, I'm going to encourage you to pause the video, set up your table, identify the end behavior, and then see how you do on your own. Then unpause the video and check with what I did. All right, so my end behavior is that this should be going up at both ends. I have found a table of values. Now I'm going to plot the points that fit. So it looks like I'm going to be able to plot these 4 points, and I'm going to do my best to connect the dots. So I'm going to go ahead and plot those points. And I need to remember that end behavior when I am connecting. There we go. Now, I'm hoping you're a little curious, what does this graph actually look like? So here is our sketch, and here is the actual graph. Now, where it's changing directions, I want to point out, is not at the exact values that we made it change directions. We did our best with the graph that we had, but the basic shape is the same. We can get an idea of a few points like the y-intercept and the x-intercept. We do have both of those on our graph, and that's a really valuable tool. Now let's look at the exact graph of the function to talk about where the function is increasing and decreasing. And we talked about this with quadratics, but we're going to focus on it now, looking at a different type of polynomial function. So if we stand on the far left side of the graph, we are going down. We're going down until we get to this particular x value. Once we get to that x value, we start going up until we get to 0. Once we get to 0, we start going down again until we get to this x value down here. And then from that x value, we go up, and it goes up forever at the end. So what we're going to do is we're going to take each of those colors, and we're going to identify those as our increasing and decreasing interval. So we go down first from negative infinity, because there should be an arrow here, from negative infinity until we get here. Here, where that is negative 1.088. And that is going to connect to, so I'm going to write a U because the union of these two intervals, the interval here, which starts at 0 and ends at 1.838. We are decreasing everywhere along those two intervals. We are increasing everywhere in between. So between these two values, so again, starting at negative 1.088 until we get to 0, and that's going to be connected with, so unioned with, this x value, and then forever up. So 1.838, and then up forever to infinity. So I do think it's really helpful to use color to be able to identify when am I going down, when am I going up. Think about it like it's a roller coaster, and then you're going to write those as intervals using interval notation. So I like to go left to right. It helps me just think through what I'm doing. All right, we have one last topic that we're going to cover, and then we're going to wrap up this video. And that's going to talk about sketching a polynomial function if we don't have any actual function, but we just have information about how it behaves. So here we go. We're going to focus on using some characteristics about the behavior of a function to sketch a particular function based on that given information. So I'm going to give you some tips here. The first thing I want you to notice is that we're given information about where our function is positive and where our function is negative. And what that means is at some point it has to change, right? It's above the axis, and then at some point it goes below the axis. That means that there needs to be some point at which it crosses the axes. So the very first thing that you're going to do is you're going to use that information about where it's positive and where it's negative, and specifically where it's changing, to plot the zeros on your graph, just like when we plotted the x-intercepts. So if f of x is positive between 2 and 3, negative 2 and 3, and 5, and I'm noticing those same three numbers down here, that means at x equals negative 2, at x equals 3, at x equals 5, it's changing from positive to negative or from negative to positive. So the first thing we're going to do is we're going to go ahead and go to the x-axis, and we're going to plot those as x-intercepts, negative 2, positive 3, positive 5. So step 1, plot the zeros, the numbers where we're changing from above to below. Now the other thing that's going to happen is if I'm changing from above to below the axes and whatever my graph is looking at, that means sometimes I'm going to be increasing and sometimes I'm going to be decreasing, increasing, decreasing, and that's going to keep changing. That's what we're being told in this information here. Those numbers where it is changing, the x values where it is changing, those are also important. So at 0 and at negative 4, at 0 and at positive 4, we are changing from increasing to decreasing. So the way that I help myself remember that is I actually plot dotted lines at those two values. Not because they're asymptotes, not because they're axis of symmetry, but it helps me remember that when I get to one of those dotted lines, I need to change directions. If I was increasing or going up, then I'm going to start decreasing and going down. So these are the first two key steps. Then you just need to figure out where you start. And where you start is always going to be related to negative infinity, because that's what's happening over here on the x-axis. As we are furthest to the left, what is our graph doing? So we're going to look up in our increasing and decreasing, in our above and below, and we're going to figure out where do we start. So where do I have negative infinity here? And I'm going to go ahead and circle those. I have a negative infinity here. This means we start below the graph, right? Because it says f of x is less than 0. The function is below the x-axis. And it's increasing. So I'm starting below, and I'm starting by going up, like I'm walking uphill. So I'm going to start my graph below the x-axis, and I'm going to make it go up. It's going to go up and go through the point that I drew, through that 0. But why did we draw a dotted red line? Because when it hits the red line, it's going to change direction. So now that I hit the red line, I'm not going to go up anymore. I'm going to start going down through the zeros until I hit the next dotted line. What is that dotted line telling me? It's telling me to switch directions again and go back up. So we're plotting those zeros. We're plotting our dotted lines. We're figuring out where we're starting, and then we're sort of just playing connect the dots. When you hit a dotted line, switch directions. Make sure you pass through those zeros on the x-axis. So if I asked you, look at this polynomial that we just graphed, and I asked you to tell me what is the degree, is the degree even or odd? Is the leading coefficient positive or negative? You should be able to say, well, since it's behaving like this is an odd function. It's not symmetric. Both ends are pointing in opposite directions. That's what odd functions look like. So the degree would be odd, and the leading coefficient would be positive since it's functioning in the same way that x cubed functions. I'm not saying this is x cubed. It doesn't look like it, but it's behaving in a similar manner. All right, I want you to pause the video, rewind it if you need to rewatch number 11, and see if you can set up number 12 on your own. First, by just finding the points and the dotted lines. Then see if you can figure out where you're supposed to start, and then connect the dots. Then unpause the video and see how you did. All right, so first I want to look at where I'm changing from increasing to decreasing. Where I'm changing from above to below the axes. Those magical numbers are -4, 0, and 5. So I'm going to plot those. Those are my zeros. This is where I'm changing from above to below or below to above. Now I want to figure out where is it changing from going up to going down, like a roller coaster. That's happening at -2 and +3. So I'm going to make a dotted line at -2. I'm going to make a dotted line at +3. So increasing and decreasing tells me where it's changing directions. I'm using dotted lines for those. F of x greater than 0, f of x less than 0 is telling me where it's changing from above to below the axis. Those are giving me the zeros. So now I need to figure out where I'm starting. Well, I'm starting decreasing because that's where negative infinity is, and we always start on the left, and I'm starting above the x-axis. So I'm starting decreasing, and I'm starting above the x-axis. So I'm going to pick to start right here. I'm going to go down through that point until I hit the dotted line. I'm going to curve back up, go through that point until I hit the dotted line, and then I'm going to go down forever and ever and ever. This would also be an odd degree because it's not behaving the same way. This would be even. It's not behaving the same way at the endpoints. It would be negative. The leading coefficient would be negative because it's backwards. It's pointing this way as opposed to the way it's pointing in number 11. So we covered a lot of stuff in this section. We talked about what a polynomial is and how to determine if something is a polynomial and identifying those key characteristics, the leading coefficient, the degree, the type. Then we looked at how to evaluate a polynomial, just plugging values in, and how to describe the end behavior. And we used those two things to be able to sketch a graph. Then we used a more precise graph to define where a function is increasing or decreasing. And lastly, we tied it all together with creating a sketch of a function that we don't actually have the function for, based on the information about where it's increasing and decreasing and where it's above and below the axes. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.